Yeah. Okay. Hello everyone. Welcome to today's ICON seminar. Today it's our great pleasure to have Dr. Tingnan Zhang from Google DeepMind presenting Gemini Robotics. And Dr. Tingnan Zhang received his PhD degree from Georgia Tech in physics. So Dr. Zhang is actually trained as a physicist, and now he's doing the cutting-edge AI in one of the frontier AI labs. And Dr. Zhang right now is a staff research scientist at Google DeepMind, and he's a pioneer in applying reinforcement learning to robot locomotion. Their work on Sim2Real back in 2018 won the Best Paper Award at RSS, Robotics, Science and Systems. And that's one of the earliest attempts to bring Sim2Real, this concept, to robot locomotion. And after that, it's become one of the key enablers for reinforcement learning of robot locomotion and manipulation. And recently, his work has expanded to explore how vision language models can enable true generalist roboticists. We know reinforcement learning can be used to achieve specific tasks, and now he's moving on to generalist capabilities. And he currently leads the whole body control team at Google DeepMind, where you saw some impressive humanoid demos with promotion ads were the videos of Gemini Robotics. That's actually Dr. Zhang is actually behind those important levels. Yeah, and now their team is developing teleoperation solutions and integrating visual language action models with humanoid robotics. Yeah. So now let's welcome Dr. Zhang.
Thanks, Ian, for the introduction. Yeah, and I'm actually pleasantly surprised by the large audience, and I found a lot of people are still standing behind. Yeah, so let's get started. So a lot of the contents actually, due to our company's policy limitations, I can only show some limited technical details into what we have been doing. But I hope that I can make this talk a little bit fun.
Share screen, so Zoom.
Okay, so let's say we'll do it here.
So if you see the image,
it would be that second screen, right? Then there we go.
Yeah, now it's good. Yeah, it's good.
Thank you. Sorry about that. Okay, no problem.
Thank you.
It's all set? Okay.
Yep.
Yeah. So yeah, due to, as I mentioned, due to the company policy, there's a limited amount of true technical details that I can share about what we did in order to make the Gemini Robotics work. But however, I do want to share some of the insights and open research questions that we're still tackling with, and you can get into some ideas on what are the important research questions that we're trying to tackle to enable true generalist robot that can work everywhere. And I also want to make the seminar a little bit more interactive in the sense that I welcome you guys to interrupt me in the middle of the talk and when you have some questions, right? So it's not just that I'm talking about the stuff and you're just listening. If you have any research questions, etc., related to this topic, you're welcome to ask. And also we can leave quite a sizable portion of time to have some Q&A, such as, for example, I know a lot of people might be interested, hey, what we do, what we're doing there in the daily life, and what kind of, what does the research look like in industry, and how maybe some people are interested if they want to also join the team or join the industry research lab, what it takes. Let's get started. All right, so it has been a while, actually. I was planning to deliver this talk last year due to all the TSC interruptions, other shenanigans. I wasn't able. And I would say the content of this, still, a lot of them are quite relevant, but we are working on towards the next version of the Gemini Robotics. I think it has been almost like more than half a year. And at that time, we will only have like Gemini Robotics 1.5 in the ER 1.5. But now, since a couple of days ago, we also released the ER 1.6. So in this talk, I'm going to include some of the newest content from the next version of the ER model. And so meanwhile, we're still working on the next version of the Gemini Robotics. Let's get started. So the mission of our entire team here is to the AGI in a physical world, right? So we can have a very capable, intelligent physical agents, and that takes the embodiment of robots, but that can do a lot of tasks and be helpful, right? We really want the robots to do very useful tasks. And to do that, we defined a few different axes to measure our progress in this, right? So here are the 5 pillars that we care about. And
That's fine.
okay, great. So, dexterity. So what do we mean by dexterity means that what kind of complex and nuanced tasks that the model can perform, right? So you might have seen that the model, even with the parallel grippers like Aloha setting, is able to even tie shoelaces. This is what we mean by dexterity. I'm not talking about juggling. These are different depending on whoever defines this problem. They can be called dexterous, right? But yeah, they are valid tasks, but not something that we're currently focused on. We'll be focusing more on the day-to-day tasks that will require some nuanced, very complex manipulations and generalization. Right? So the model should be, in order for it to be a truly physical agent fashion, we want it to be that it is able to solve a lot of tasks, not just a single task. For example, we can collect maybe 1,000 hours of data just for the tying a specific shoelace, but maybe it's only good at tying that particular shoes, and if I change it to a different shoe, or it changes to boots and it stops working. And that's not something we want, right? We don't want it to be so narrow. And instead, we want our model that would have recipes such that it can maybe not out of the box can solve all the problems, but it can solve a sizable of the problems, and that such that it can be learning new tasks relatively easily, right? So for example, maybe through our pre-training of our models, and now you have your own task, which you've never seen before. It maybe is only going to do that a little bit, but maybe you give it an hour, 2 hours of data, it is able to do that at high reliability, right? And safe interaction, right? It's a physical agent. You don't want the robot to suddenly do something pretty crazy, even though it could be in a very out of distribution scenario. And embodied reasoning, right? So what happens there? What happens is when a physical agent performs certain tasks, you want it to be able to reason about the task. What do you mean by reason? For example, it has to know that it's either doing that successfully or not, right? And it will have some capabilities specifically to the embodied reasoning models we have about some kind of planning and a physical sense about, okay, what I should do in order to make this task happen. Maybe there's a task that requires multi-steps, and each of the steps requires some physical interactions. And we want our model to be able to plan this out. Right? So such that in the end, you can just say, hey, I wanted this to happen, and then it will do the task from principle. So that brings the last pillars about this agentic capability in a physical sense. Right? I know agents has been pretty hot word this year, especially people begin to see how with the proper harness and the properly trained model, there are a lot of coding tasks seem to be already being able to be solved, right, in the end-to-end fashion. I'm pretty sure maybe a lot of you guys here are using cloud for your daily coding. It's like coding, the way of coding has been fundamentally changed. Yeah. And we do hope that somewhere in the future, not yet, somewhere in the future in the physical world, we can also do the same thing. We just sit there and tell the robot, now I want you to do this, and maybe give it a demonstration. Now you can figure out, right? But there's still a way to go. Okay, so in terms of where we are, so in the previous, talking about the first version Gemini Robotics release, we have been doing, we're able to achieve some aspects. So especially we show that these robots can do a large sizable tasks. And since some of them are pretty complex, as I mentioned, there could be this zippers and then put something out of it, right? But in terms of its whole capability range, and there isn't that much about. So it has showed, we would call that shows the signs of life. Doesn't mean it's anywhere close to where we want it to be, right? So, and then again, in the next version, that is Gemini Robotics 1.5, we're trying to push along each of the axes that we have defined and make it much better, right? So for example, this generalization, there are different ways to measure generalization. It can be saying this robot is doing tasks we've never seen before, or it could be that means that this particular model can even be applied through multiple embodiments. So for example, maybe you have a biome robot, maybe you have a humanoid, right? They all come in different shapes, geometries, and physical properties. Yeah. And maybe some of them are using dex hand, some of them are using a single parallel breaker, right? And what we hope is that we can figure out a recipe such that the robots can kind of being deployed to each of the embodiments if we have the data that can do a lot of things out of box. Right? And also we're trying to see in 1.5, I'm going to show you that some of the agentic stuff by orchestrating the embodiments linking together with the action model there. All right, yeah, as I mentioned, so in the Gemini Robotics 1.5, what we did is like we truly are making, the both of the words working together. So that's we're going to have the ER model, which has been, it's a specialized Gemini model such that it is compared with the normal out-of-box model, is better at a lot of this physically relevant tasks. For example, if you ask, hey, in this picture, what are the coordinates of each of the objects I'm interested in, then it is able to do that. We actually were able to demo that last year, somewhere, yeah, such that you can ask even open-ended query questions. You can even see, for example, I actually tried this with something very fancy. It's like in some of the Southeast Asia, they have the Buddhism, like 1,000 Buddhism, right, being in lines. I actually asked the model to say, can you just pinpoint all the Buddhas in this picture? And it's able to just like almost generate a dense set of points to mark each of them. It's pretty amazing at all these open-ended query questions. And some of the capabilities that are quite relevant for orchestration also includes, for example, not only object detection, like trajectory, and the state estimation is important. Like, for example, is the box open or not, right? If it is mistaken at this, then your task and will not be able to be successful, right? Maybe. And then there are also something very important is about task progression prediction, right? So it is now roughly how many steps are still needed for the task to be successful, right? So it can be able to plan this task in a very coordinated fashion, right? And the ER model is sitting at the top level, and it's different from an action model in the sense that it still is it's a conversation agent, right? So that you can have a through real-time audio conversion and talk to it and ask it to plan a long horizon tasks. And then the Gemini Robotics, the VLA model, will be sitting at the bottom as almost a two calling, but it's a little bit different than the primitive two calling in the sense that, so usually you can think about there are many different granularities so you can break down the system, right? You can see that my granularity is I want this model to be only good at one thing. I can have a lot of models. This model is pick. That to call is place. That to call is doing something along this line, move from A to B, right? So they all have their constant pros. The pros are that such that you can build and refine each of the primitive actions such that they're pretty robust. And the cons would be that usually not all the tasks that you're interested in can be even broken down in a clean way like this. If I ask you to say, hey, are you able to open a zipper? What do you mean? You want to build a primitive just to grasp that zipper and slide it? It's very hard to specify in a very specific way. So for some of the very nuanced, especially if we're trying to deal with more dexterous tasks, I mean, with some in-hand manipulation, it generally is pretty hard to define any primitives that can do this, right? So instead, what we are our approach is to say we build a more kind of a generalist action model that can also be conditions on relatively open-ended queries, right? You can say just grab that zipper and open this bag, that it can be able to do that. Of course, this approach comes at its cons that it would require a lot of data. I'm talking about I'm talking about the hours, probably beyond the millions of hours of data for it to be truly achieving, to be a truly generalist, right? And nowadays, we're still looking at the scaling law along this dimension and trying to understand how much data we can push into the model such that it can be at the performance at the level of something like the GPT or the LLM. All right. So let's talk about the VLA, right? So compared with the previous version of Gemini Robotics VLA, the 1.5, we did some upgrades. So one of the selling points there is that we can have a single pre-trained model that can actually work on multiple embodiments. So here we're showing about Aloha, which is where we started, and we added humanoids. The humanoid actually is using a more dex hand, that's 5 fingers. And we also have a different biome platform called Duo for Duo, right? And you can also see that the setups are pretty different, right? So for the Aloha, we're mostly interested in some of the tabletop tasks. Then for the Duo Brinca, we have been looking at a lot of this gear and some more industry-related settings. And for the humanoids, we are looking at a diverse range of tasks from vertical to horizontal spaces, and mostly focusing on the home settings. Okay, let's see. So here are just some of the showcases to see that a single pre-trained model that can do probably, so we're talking about all 100 issue tasks on the 3 different models there. And that includes some of the pretty nuanced tasks, like, for example, inserting the USB cable in the computer, which will require some kind of precision there as well. Yep, as I mentioned, it is actually a single checkpoint. Compared with 1.0 time, we have to do quite a lot of specialization. For example, if there is a humanoid, then you probably need to train a lot on the humanoid data. If it's Aloha, you train on a lot of Aloha data. And now at 1.5, what we're able to achieve through some kind of recipe tuning is such that the single pre-trained checkpoint is good at identifying its embodiment specific features there and leverage that. And also it has the capability to absorb all the data that we have collected so far. Right. So there are some of the ends, as I mentioned, the generalization can be measured in many different ways. In multi-embodiment is one way we measure the generalization. Another way would be looking at a few axes, including, for example, what we call instruction, action, visual, and task. Instruction generalization is a little bit relatively simple. For example, if I gave it a different language, right? If I'm Chinese speaking, maybe I can just say, bring it up in Chinese, or if someone's Russian speaking or something. And we can also tune the language instructions in a way. For example, if you're just naively using something like a clip, then you probably are only going to associate that particular embedding of the word with a particular skill, right? But here you can say, maybe pick up, you can say, oh, I wanted to bring that closer. There are many different ways you can specify the same task, and it's able to do that. And when we're talking about action generalization, this is still a little bit more early stage to think about. I'm not talking about tasks it never seen. So for example, if the robot has been trained in many different tasks, but it never sees how to, let's think about how to juggle, right? And then you won't expect it to be able to do the juggle at all. Maybe it is because through some other motions, there are segments that overlap. You can try to do a certain mimic the motion, but doesn't mean it is able to do that, right? But here, when we're talking about action generalization, we're always thinking about, for example, if you collect the data in a certain way, but then, so for example, you have a USB insertion that is on the horizontal. But now what if you rotate it and put it completely vertical? Is it still working, right? Something along that line, right? And it has turned out to be one of the hardest places to generalize, which indicating there are still a lot of action data that we can still need a lot more action data than we have today, right? Along that dimension. And so the visual generalization, this is the benefits of using large models such as Gemini. Right. Basically, the Gemini has been pre-trained, even before the robotics pre-training, is pre-trained with internet data. That means these visual encoders, they have been seeing probably, I'm talking about maybe even trillions tokens, right? And such that if you change the lighting condition, a whole bunch of other things, it probably doesn't care. And I'll be showing something very interesting about is that you can even train a checkpoint that are completely using real data, and you can do semi-eval, right? So the semi-eval, we're not trying to make it looking realistic. You can tell as a human, you can say, oh, this is the same as real. And you can still do that. And there's a good correlation there. Right. So that says the benefits of using the large scale pre-training using internet scale data, especially visual generalization. Right. So it's no longer sensitive to just, for example, if you put maybe a carpet in the background, suddenly the model doesn't know what to do, right? It actually is still robust to these kind of perturbations. And the task generalization is a little bit tricky, right? What I mean there is, for example, we ask the robot to say, hey, maybe it's trained on a diverse task, but now if you wanted to do something like putting the basketball, like doing a slam dunk type of thing, it kind of is able to do that in the sense that you can say you can combine like a novel objects, or you can even just create some kind of scenario where maybe the motion it knows how to do that, but you've never seen this kind of a task being trained. It is able to perform this kind of tasks. Like instruction generalization, as I said, multilingual support, and that also comes just from the Gemini's pre-training. Right? We didn't really, in our robotic training, include multilingual instructions. So somehow within Gemini, these embeddings are closely matched. And if you only train in our instructions, are just all in English, and you work with multilingual. Yeah, new objects. Some of the objects never appear in our own data in-house data collection.
I'm sorry, I'm not sure if it's okay to ask in a high level, how do you train that? Or are you going to talk about this or not at all?
There are some certain details that I cannot talk about. For
Which
example,
is high level.
Yeah, very high level. Yes, yes. So high level, there are a few things you need to do. Right, you have to do the embodiment alignment. Right, something what we call motion transfer. Right, you have to think about what if you have an embodiment that your output dimensions are not even the same. So how do you do that, right? Some kind of padding is definitely necessary, right? And so then there will be certain things about, what kind of task you train on. These are actually all the secret sauce. Basically, they're also on the data side, right? So do you do naive BC or you want to have some more nuances on it, right? If you do naive BC, there's an upper bound on where you can achieve. Just so that's the most I can share about, right? You have to do the pre-training in a more diverse way than people would be imagining.
This is more like a reinforcement learning type of thing? Or?
No, these are all like large model training. Yeah, I'm going to talk a little bit about reinforcement learning in the later. But the reinforcement learning with large model, it comes with its own very nuanced details there.
I see.
Right. Okay, so as I mentioned, right, so with a large scale pre-training and with our new recipe, what we call the motion transfers, we're able to achieve in many different categories, right? Yeah, so that's one example, standard white paper with a rubber. I don't think we have any task close to that, but it's actually able to perform something like that. Yeah. Of course, one of the limitations are like doing our data collection now, they do the teleop. These data, they probably don't include anything about post-torque control, right? So essentially, if you wanted to say, yeah, press gently on the egg, that probably won't be able to do it. It's just still not anywhere in this data. Right. And yes. So yeah, there are some of the studies that you just mentioned in the motion transfer. So essentially is that what happens there is when you train on multiple embodiments, we also do see some of the benefits of task sharing. What we mean is that if you say there's a task that is only being trained on a certain embodiment, and then later we actually show that it is able to be performed by different robots, even though in that particular robot's collection setting, this is never seen. I'm not talking about just the pick and play, I'm talking about the entire thing is different. For example, the Aloha is being trained on tabletop because of its setting, right? But then later you can just put the two boxes from the Franken dual setup, and it's still able to do something there. Yep, let me see. You see here? That's what we mean by this motion transfer. So entire data setup is being collected on the Frank dual, right? And then we say that now someone is like, okay, what if we just put that two boxes there and see how Aloha can do that? And it turns out it's like, yes, although a little bit less smooth compared to with the original embodiment, but it kind of still does that. And so let's see the other example there. Yes, and this, yes, and you can see here. So we ask the Aloha to actually do this insertion task. As mentioned, it's also being exclusively collected on the dual platform. Even though sometimes it does drop in the physics about because it's something that it has never seen before in this like native domain. see. Yeah, so this is show the other way, right? It's just not a one-way transfer, and actually there are. Let's see. Yeah, you can see the reverse transfer also works. So it means that through our own motion alignment and all these like little details we put there, it is able to cross embodiment transfer. And that was a big selling point for Gemini Robotics 1.5. And here, and to make it even more general, you can think about what about even if we change not only, because you can argue to say the Aloha looks still kind of similar to that rectangle, right? But what about the humanoid? The humanoid is very different in two ways. One is that the humanoid itself is and the difference are one is using a dex hand. So that dimension that you need to control for the hand is going to be very different from the gripper, right? One is at least somewhere between 5 to 10 degrees freedom, and another is only like 1 degree frame of gripper. So the humanoid itself, even for the upper body, contains much more degrees freedom, right? And because also the humanoid, one thing that people didn't realize is like the viewport is not stable. Sure. Yeah. So for the humanoids, this upper body, the torso, can twist and also pitch like a real human, even though in that particular case it's tethered there. And also the viewport is doing slightly, so because it's a viewport limitation, it has to do a lot of like head movement, right? And so this is a little bit subtle. You can actually see there. And for Aloha and Duo, you essentially could think about all the cameras are fixed. So there is this kind of egocentric differences between the different embodiments in this particular case. And somehow you can still see the motion transfer that happens in between the different robots.
Excuse me. None of them are teleoperated, right?
These are all autonomous, execution. Yeah, but certain, of course, we have to collect the data, maybe not exactly the same, but some of the tasks are collected on the different embodiments.
And the data is collected on teleoperation.
Yeah, so when we collect data, so we rely on teleoperation. So yeah, and for each of the embodiments, they have their own teleoperation system that are not shared. So their data collection, the way they're doing the data collection is very different. So for example, for the humanoids, you don't have a setup behind the robot, right? Because you cannot see how to go through the VR. You actually need to see through the robots, right? For the Aloha and for the Duo, you can still kind of see, look around from a teleoperator's perspective to perform this kind of process. Yes.
I have a question. Like when you change the embodiment, is there like a planner that knows that the embodiment has changed, or does the model itself adapt to change the low level control of the?
Yeah, you do need to change the config a little bit. When the config is like, you need to kind of prompt in a way, letting it know what kind of embodiment is being used.
So the model itself adapts the outputs to the different one?
Yeah, then it will adapt. Yeah. So yes, there are configuration changes you need to apply. Otherwise, it's depending on how you configure, because the model only sees the camera images, right? And there could be this kind of confusion on what it needs to output.
Is it via instructions only, or do you make other configuration changes?
So the instructions are something very general, right? You don't need to tell, oh, you're a humanoid and then to do, no, not like that. But maybe that's also an interesting research directions.
So for the embodiment transforming, do we need to do the post training to match the actual UX or to do the patching and the masking?
Yeah, there are some little nuances, but I don't call it post training. It's all a single training recipe, right? So when I say pre-training, post training here, so yeah, there are actually two different types of pre-training. Pre-training, we can say the Gemini pre-training that basically are trained not on robotic data, right? And then the Gemini checkpoint can be used for robotic pre-training, and this pre-training already includes all our recipes, right? Including how do we do the alignments between the embodiment, how do we add the different tasks for the training. And then when we say post-training we're going to show some of this is, but some of the certain tasks after pre-training is not going to be able to do that well, simply because of the sheer complexity of this task, right? You need some more specific data, right? And it could be because in the pre-training maybe we should include even more data, right? But due to teleoperation, there's always a limit on how much you can collect within a certain amount of time, right? So maybe in a couple of years when we say maybe we can have all the internet scale of the action data, like what we have for the language and visual data, then maybe it can truly be all about to almost anything. And of course, there will be an argument saying that maybe still there will be tasks require fine-tuning, and that's okay. What I mean is, like, for certain tasks, for example, even human, if I watch someone doing, I like skiing a lot, but if I just ask people who never ski, say, now you watch the 10 hours of ski, then now ski, it's probably going to collapse right on the first round. So there are going to be nuances about the tasks that you cannot learn just through video, just through saying something. Even some of the tasks are not teleoperatable, probably you need to learn them through RL and other ways, right? So that's what I mean. So for very complex tasks, even human, we have some post-training that will require hours, right, just to learn how to do that task properly. So I do feel that as long as we have a general good enough foundation that you can learn fast, right? And I would call that's going to be a solid recipe that can be very useful in the real world. Yeah. All right. So another invention that we actually added, and that's the details I can talk a little bit more, is that these VLA models actually have its own thinking traces. What I mean is, like, so essentially, if you think about the VLA's input is a image plus some kind of string conditioning, right? And however, what we found is, like, you can also let the VLA itself, because it's also a visual language model, the language part can still be used in a way that it can kind of update its own prompt, right? So for example, if you give a more general instruction, say, oh, doing something like picking up something, then it can actually itself be to describe what kind of motion is needed in order to achieve the task, and kind of like prompt itself. When the prompt itself, usually what we find is, like, it is able to actually does the task better, especially in the more difficult, more nuanced settings. Okay. So far I've talked about some of the innovations we have done for Gemini Robotics 1.5. That includes multi-cross embodiment transfer and our way enable the low-level models also think about the changes on prompt to improve success rate. And then I'm going to spend a little bit of time also on this orchestration part, right? That is the ER 1.5, and I'm also going to talk about the ER 1.6, the delta from 1.5 to 1.6. And there are some pretty cool demos there. Okay. All right. So the embodied reasoning, as I mentioned, is a little bit higher. If you think about the system, right, we're still dealing with a hierarchical system. There is the system 0, depending on which one you call system 0. Usually, when I say system 0, I'm talking about lowest level controllers, right? So, for example, we're talking about for Aloha and all the stationary robots, you only need a very simple system 0. That means you can follow the arm motions, right? If you just say move the arm to X, Y, you can move the arm to X, Y, that's fine. But if you want to deal with something like a humanoid, right, and your system 0 at that point needs to be a little bit more smarter, right? For example, it has to be not only reach to that position, but not collapsing or trip itself, right? And that itself is its own research. We can talk about a little bit about that later. And then there's a system 1, which we usually call the VLA, right? That it can do a lot of more dexterous. It can achieve the task in a more nuanced fashion, right? It can figure out the complex motion planning is needed to achieve these tasks. And then on top of that, we call system 2 is the ER, where the ER model sits. It should have the capabilities to do more long horizon planning. It has to be reasoned about the tasks to output the correct subtask, to divide subtasks, and it should be able to do successful success detections, so such that we can integrate that into a agentic system to do orchestration, right? And yeah, so there are some of the embodied reasoning here. Here's how we are measuring this generality in embodied reasoning score, right? So, and when here, something like GPT-5, it has a lot of general capabilities, but often you see the big models when they're trained, they're actually not being specialized enough for a lot of robotic tasks. If you ask it about even something sometimes as simple as, is it left or right hand? They're going to be pretty confused, right? And if you ask you to say, is the man on the left or on the right, they often get confused. So, but for robotic tasks, we care about the spatial relationships, about temporal relations, a lot of things. And we also care about a lot of these real world applications. For example, I'm going to later show you that if you ask, I don't know if the latest model, by that time you ask the model to read a clock, it's slightly better than random guessing, right? But it also, we notice that a lot of this, it often has a preference to say what time it is. And people hypothesize maybe it has been trained on whatever the Apple Watch, the clock, and so which is always, this demo images always show the same clock. So it has a bias of outputting something, right? So that means it doesn't really learn anything about the reasoning about this, right? But we do care. And actually, if we have a deep partnership with Boston Dynamics right now, and one of their tasks is for the spot, right? Spot has been used in construction industry settings where you need to go to different places to even check for meters, right? We can't just let the models randomly guess a meter. It has to be reading and understanding that, right? So there are some special applications when we do our robots, we do want this VLM that to be able to perform more than just a conversation about, right? So a lot of times the issue with after just the pre-training of these models, like all non-specialized, they're pretty good at entertaining you, right? It's like, okay, telling something sort of relevant, sort of irrelevant. And nowadays, they're also pretty good at generating images. But when you are just using these generic functions, you don't care about accuracy. Even if you say that generate human, it generates, there's maybe one more finger, it's okay. We can live with that world. So here are some of the examples demonstrating the ER capabilities. As I mentioned, that it has many kind of a physical sense or a spatial sense. Right? You can, for example, you see here, it can plan a trajectory by itself. So essentially, you can try to see if you can prompt the ER model to say, maybe I can do navigation out of the box, right? Just to say, give me a trajectory that is collision-free. That's one example there, right? And then it also understands physics in the sense you see, what about the falling trend of the water, right? So it has to be able to kind of understand, maybe it's still pretending to understand the physics, but it's definitely much better at this type of task than other models we have seen, right? And it also reasons about, which is heavy, and then you can think about, so now you can say, pick up the things you can pick up. Then you won't try to be so pick up something that is beyond the capacity of a particular robot, right? Yeah, so there are kind of more other examples here. And so one of the things we really like about this model is this accuracy. You see, draw some circle, almost like we're asking to draw a circle along the rim. And it is able to be pretty accurately pick up that, and also find out all the matching socks, right? There are a lot of interesting capabilities that has been emerged through this ER training. So some of the students asked me about to say, hey, they noticed that some of the model after specializing, like a video shows something about this navigation model, but then it only wants to output navigation scenario. So for example, if say even there's no human, you're going to say it's trying to say, oh, maybe there are two humans, right? These usually indicate the models through post-training or some stages are not very well, so they haven't seen enough negative examples. Right? So basically, there are, for these large models to work, some of the insights, what I can share is like, it's very important how you think about your training data and your eval data distribution is, right? If your training data is not diverse, you won't expect it to generalize. And if your eval data is biased, you also won't be able to really measure the performance of this robot, right? And also, sometimes both positive and negative examples are important. Otherwise, you'll be saying, if there's no human and you're still trying to predict that there's a human, right? Yeah, so there is just a benchmark on the specialized capabilities like pointing, spatial reasoning, and the steerable. Right? And actually, this is already updated. So I'm going to show you later on how there's actually a big improvement from ER 1.5 to ER 1.6. It's actually getting much, much better. And we probably would call it like industrial ready. All right. And yes. And then one of the capabilities that we developed through ER 1.5 is what we call the progress understanding. What it means is like you give a series of images, even the inputs can be randomized. So, right, so think about this. If I give the video, but I'm not fitting the video as is, instead, you can randomize all the different frames and ask it to reorganize the frame. It actually has the capability if you give it all the frames, basically saying, okay, this frame should be before that one, but it can output the correct sequence, kind of, right? So, but now think about what this can mean, right? So one application people will think about, actually, there was years ago, we have a paper with Jason Ma, who is now the founder of Dyna. So his idea at that time is like, what if you can reorder, you can let the large models to detect the progression of the particular task. You can think about it, if you can do that reliably, now you have sort of have a free general reward model for your task, right? Because that progression itself, you can think about that's a reward. And maybe that's something that has been using up to till nowadays, right? How do they actually do the fine tuning? And you can also say, if you have a general order of the progression, that allows you to maybe to get something for free, including maybe you can do something smart BC, you can do some kind of filtering based on if a particular thing, if trajectory is a good or bad, right? You can have some kind of rating. So because apparently deviated trajectory means your reward or your progression would be stalled or even going backwards, right? So some things that you can think along that line. And there are some other capabilities we can use, like multi-view success detection, which is quite important, right? So if you want the model to be an orchestrator in the agentic setting, you can say, then sometimes a single view will be blocked, right? Depending on, so if the hand is on top of that, then you don't know if it is being grasped until the other hand is being out. So it should be able to leverage multi-view to do more robust success detection. Yeah. And Fremont shuffling that I talked about. And yeah, let's say here are some of the benchmarks just showing it's there, but these numbers are not where we want it to be, right? So ideally, eventually we want it to be all in upper 90s, but there's still ways to go. Yes.
Sorry, can you get rid of that small?
Okay, I'll do that.
Okay.
Go ahead.
Okay, thanks. All right. Yeah, some of the details there on how the token budget, but yeah, let's bring up this one. So, all right. So now let's think about. Okay. Second. Yeah, so as I talk about the two components, there is both the ER model part and as well as the action part, right? When you combine them, now you can think about you build a harness around them. Now you can get the same agentic system, but now in the physical world that allows you to autonomously do a much long horizon task. Of course, we can define what do you mean by long horizon, right? So when we're talking about, usually when we define about normal short horizon task, we're talking about maybe just pick a place or doing something, or maybe open that box. This will be considered a short horizon task. But now if you wanted to say, I want to pack a lunchbox or I want to put ingredients, put all the ingredients, find all the ingredients from the kitchen such that I can cook something, right? Then that will require multiple pick in the place and also reason about what to pick in the place, right? You have to be selective. And for this task, sometimes depending on the complexity task, we may need to fine tune some of these, right? And yeah, there's another example of showing, for example, what if someone. So there are some of the ideas to show that with the agentic that we are able to do a lot of tasks with much more complex and nuanced tasks, including, for example, you say, hey, I have a nut allergy. Before I come to the US, I never know such a thing. But after I come here, I realized a lot of people with different types of allergies, and they have to each check to say the ingredient to say, otherwise the people can sometimes die. So then you wanted to say, if you just ask action model, sometimes it's not pretty picky. You say, oh, I want to pick up the bar. Sure, I pick up a bar, but you won't read the label, or you won't think about the label, right? But now you want to say, I want to pack allergy-free, not free lunch boxes, and you have to do a little bit more reasoning about do I pick up the right thing? And so do I recognize this? Is it safe? This kind of reasoning and orchestrate everything together. And the complexity also comes as all the different items are at the very different locations, right? So some of them on the shelf, some of them maybe you have to open the drawers in order to just retrieve that. So yeah, that's a pretty nuanced task. And also demonstrate how amazing our data like human, we can do that even without too much thinking. Right? So there is still a gap between what we can do today with these models and where the humans are. Yeah. And so yeah, here are some of the thinking traces that output from the agent, the physical agent. Hey, because what we can do here based on the, it also knows the location, by the way, because depending on where you serve model, where you call the model, it actually oh, this is the California, then there's a trash law of certain kinds, so you have to sort things in a different way than maybe from Illinois. I don't know the details here, but right. And then you can figure out all the correct order and the stuff to sort, right? You see, yeah, I don't even remember that instruction sequences, just I listened to once. But we just want to show that this multi-step instruction following is available for free once you have this agent system altogether. Yeah, these are all policy running. Right. Anyone remember what's the next instruction? Yeah, the background is saying something. Just to let you know that, so this is almost like a prototype of how we can imagine in the future physical agentic system would be like. Maybe in the beginning we can even confine it to certain subtasks, or even we can confine them to be tabletop tasks. But if we can get the reliability as well as the usability there, that would be a pretty amazing, useful setup. Let's see. All right. As I mentioned, so since it has been quite a while since we released the last model, actually recently we also released the ER 1.6. And the difference will be mostly as its accuracy and more, even better spatial reasoning and accuracy at industrial level. I want to see. So, for example, the single, as I mentioned, right, in the 1.5 ER 1.5, we're able to do some success detection. But if you look at numbers, they're somewhere in the 80s, but now a lot of the numbers has been pushed to upper 90s, and that's something we wanted to see, because that means you'll have a less chance, have a higher success rate when you are using this as your orchestrator or as the agent. Then here there are some of the other components that you can see, right? So, for example, we compare with ER 1.5, a lot of this, like pointing, and has also been upgraded, especially in a very messy environment. So, for example, you see pinpoint the tunings, and if you just look at the distribution of how it is able to follow the instructions, and some of the false positives that there, especially here, has been actually improved quite a lot in ER 1.6. And that's also thanks to the next version, that because from the Gemini 3.0, there is also an upgrade in the foundation model itself. And I want to see if this. Yeah, this is the recent commercial that's been released by Boston Dynamics, just to show that now it has kind of fully integrated the GR, the most released version of ER into their actual industry applications, right? So that the robot dog is autonomously inspect a lot of things as not only see, it is able to actually the gauge, to read the gauge, not just hallucinating and guessing. So yeah, there are some of these examples, just to give you more ideas on how. So it's still embodied reasoning, right? So you can see here, you can have a very simple prompt. Actually, it is able to output a lot of thinking trees and to understand the complexity, and even it has the capability of using tools to understand the exact readings and say that test the dangers, and if there's a potential danger that has been presented in some of the cases here. Oh, there it was. I hope, yeah. Let me see if I can find another video. I might have some very fancy videos. Okay. Yeah, never mind. Somehow I cannot find exactly the video I wanted. So let's continue. So far, I have been mainly talking about what is capable, what we are capable of doing today with the Gemini Robotics VLA and our VR models. But I also wanted to provide a little bit more than just showing capabilities. Right? There are some insights and open questions in the set of VLA, and we're trying to understand and even solve them. And here, so this is from the two videos. One on the left is from the generalist, and the other is from figure. Right? So if you can see, look at all the hot startups as well as what we have been doing, everyone would agree that data is the key nowadays in order to scale up. The only thing that people don't agree on is how much data. Okay. So for generalists, they claim, for example, they have 500,000 hours of real world data in various different ways. They can be from teleop, they can be from human, sensorized the human collection, what that means, for example, Humi style type of collection, or just a pure human data, right? And usually to train the VLA, you do need, I would say, at least a million hours of skill data, right? For it to be generally capable and also to build a good foundation. And then even at intelligence at lower level, I'm talking about system 0, right? You can just say nowadays, since last year, a lot of progress in the whole body control world. To be honest, there aren't that many innovations or breakthroughs in the algorithm side. So all of them are being trained in a similar deep mimic fashion. It's just the amount of hours being used. For example, I'm quoting here, figure actually says explicit that we have 1,000 hours of human motion data. And you also need high quality human motion data in order to achieve that, right? There's also a sign to show the scaling of data, right? Just at a different level, you probably need a different amount of data, right? So for example, for the lowest level, since you don't need to do any kind of hand-eye coordination, you probably don't need millions of hours data. But for general space falling, 1,000 hours each of data is already being able to achieve a lot of things. Maybe not backflip or cartwheel type of things, but a lot of things that happens in the day-to-day life can be actually achievable. And then for the VLA, it's an open question. So then the other question is like data scaling, right? So teleop can only give you that much. What I mean is like, no matter if you're the best teleoperations, if you operate the best data foundry, your scale up is by the amount of human you can hire, as well as how many robots you can use, right? And also robot-specific data will always be comparably scarce compared with internet scale data of random YouTube videos, for example, right? And then the question is, how do we get this data? As I mentioned, there are people, for example, Pi recently think about maybe we should have some kind of good enough model, then we let the model to collect data itself. Yeah. Dana is sort of doing that. The idea is like you can build some kind of flywheel once you have a good enough foundation model and it can achieve the tasks, right? And you also, but in that sense, you also have some kind of question there, right? So for example, we know manipulation. So we solved the general whole body control problem through some kind of handcrafted reward functions. But for general manipulation, usually we don't do sim to real, partially because each of the manipulation settings, there will be something different about that particular task, right? And we don't yet have what we call a generalized reward model for all manipulation tasks. Yeah, that itself is a big question. And also RL learning with large model. Right? I mentioned before, it's RL learning with large model is not as straightforward as people would think. Right? In the MLP time with sim-to-real and PPO, you can train however long with your models like MLPs, right? And they just work. But you do notice a lot of this RL algorithm, they were designed for smaller neural networks. And they're tuned for these kind of settings. And even until recently, we don't even have RL directly on diffusion models, right? Until maybe last year, they finally have something like the DPPO with the diffusion PPO. And that is also quite a complex implementation there just to get it work. Now you can imagine, in order for the RL to work with the large models, right? People have invented GRPO, that's just a couple years ago, partially because even adding a value function for this large model is in a pain, right? Do you want to have yet another large model for the value function? Yeah. And also, how many steps you can train for RL for the large model is also something not trivial. It's what I can say is pretty easy to blow it up. Right? So for the large model, it's just not as stable as the small MLPs. And even there are some kind of definitions of people talking about RL. Right? So for example, if you have some kind of general reward model progression, do you need to do RL in this particular way, like some kind of random exploration, or do you really want it to be explored on hardware? Probably not, right? And that can damage the robot pretty quickly. And one thing I mentioned is sim-to-real for manipulation is kind of underexplored area. Right? Partially due to the sim-to-real itself, the context properties, partially due to all the difficulties of really engineering a reward function. If we can get breakthroughs in both of these worlds, then essentially you can get maybe trillions of data for, I wouldn't say called free, but you can get a lot of data, right? So the reason why this locomotion problem can be kind of solved with only maybe 1,000 hours real world data, you have to also look at how much hours they have trained with the GPU time, like how many samples. Actually, the neural network actually sees probably trillions of samples during the training time, right? So it's just because we're using sim-to-real, we saved a lot of real world data. Doesn't mean this algorithm are sample efficient. They're not. And another approach to scale up would be thinking about using human. Right? So you've seen this kind of gloomy styles that you use a gripper, and hopefully that as long as you use the same gripper, right, you might be able to do a good transfer. Right? And of course, this comes back to how do you collect the right data, right? So for example, Google wants, in order to robustly achieve even like a tossing task, you want to collect them at different background, different objects, right? Otherwise, you probably would have a model that only is good at tossing a particular ball, right? So the diversity and how do you define the setup, how many hours per task you want to define for that particular, and how do you even define a task such that we can say this is a task and that is just a combination of tasks, right? These are all not trivial questions. And then how do you even filter? Say this is good data, that is bad data. And all these are kind of pretty hard questions. I don't think that has been solved. And what we can say is that now they still would require experienced engineers and researchers to look at the data to actually help with define this, right? But can we really figure out a very scalable way such that we can scale up this data? All right. Yeah, eval. One of the big bottleneck that I see in the robotics nowadays is the variance in eval. So in the large model, why the large model field can develop so fast is that the eval itself is kind of free. I'm not saying it's truly free. It's basically you have some data sets. As long as you define the data set well, You just evaluate your iteration on the data set. That's how CV has been progressed for years. That's how LLM has been developed for years, right? But when it comes to robotic, things begin to break. So generally, it's the last year they released the blogs that say, hey, we found the robotic scaling law, but that has been very controversial. The problem is that, so first, there are many different problems. So one of the problems is that they are looking at the validation loss, but validation loss is never good measurement of the closed loop behavior, right? Because what do you mean by validation loss? Your loss on what? Is it just L2 mean square, some kind of loss with your data set trajectories? But then the question is like, if they're in manipulation task, you can say have different multiple ways to achieve the task, right? You're deviating from existing data set doesn't mean it's not a good policy. It could mean it's just learns the right behavior, but it's just not the right loss to measure, right? So that's fundamentally the problem. The real evaluation is always put it on the robots, but even in that case, it can be painful because maybe if your model is so good, then you just dump the evaluation there. You put a setup there. You just say now do the eval and maybe look at the success rate. When you have enough evals, you can get a relatively clear signal on the performance. But what if your model is initially sensitive? It might work in a certain region, not in the other region. Then your eval setup will bias how you measure your progress, right? That can be a huge problem there. And you always have a fixed eval budget, right? So there's only this amount of robots and this amount of time you have. And how do you design your eval such that it can truly reflect your progress on the stuff you want to measure? And one of the stuff we have been doing or trying to look more is maybe we can do the semi-eval. They have its own nuances, right? It has their own limitations. But what we want to say is that at least for models like Gemini Robotics, because we train on the internet scale of visual data, right? It's not super sensitive to the visuals. But still, there's a difference between the sim and the real. So that if you train with real data, you can kind of do the evals in sim and get some statistics there, and it can show there's a correlation, sim to real correlation. What will matter is not that the sim to real has the same success. They will never be, right? The matter is that it has the rank preservation if you want sim eval as your way to climb the ladder, such that a good model is also a good model in sim. But is that always the truth? Right. So because your sim can also bias your eval in different ways. For example, what if you didn't really model your visuals, right? So if you use the wrong objects in the sim, it will not give you the correct signal. Or if you truly have a very terrible physical property on the sim, then you can also bias the eval. Okay, so there are some discussions as recently there are a lot of hot topics around work model, right? And then people has also begun to ask us, what do we mean by VLA, right? So essentially there are some questions on how do we want to pre-train the VLA, right? So do we want to use the backbones like the VLMs? Do we want to use backbones even like something as video models, right? They all provide their constant pros. There is some recent Stanford worked on unified video action model. So basically, they do both video generation and action generation. That might provide some benefits because you think about it. If you look at a good word model, they seem to learn some nuance in the physics in there, right? You can predict the frames and predict something quite realistically. Not everything is high fidelity, but it can do a lot of things. That seems that it has some mental model about how physics should work, and maybe that's what it needs for the VLA. But of course, we still need a lot of research into this field. Last but not least is like in order for us to be able to do this kind of work, the infrastructure and compute are quite important, right? So for example, internally we have things with the manager is that you can launch a job and say, I need 1,000 GPUs, for example. Then you can just write a few lines of Python script, and 15 minutes later, I have a job that's using 1,000 GPU. And that's, then I don't need to know details about administrative tools, how the clusters, anything. I just need to do my job, right? And of course, you also need to see the amount of GPUs and TPUs needed. So for example, you might need to say, if you think about this, each of the large model fine tuning, you guys also do some tuning with the Pi, right? So something as an order of 100 GPU, TPU is just a kind of I wouldn't say it's almost at the bare minimum that you should use in order to tune a large model. And now you have 10 researchers, each of them want to use 100 GPU. Now you are looking at 1,000 GPUs, and not everyone can afford that, right? That's the question there. And if you want to look at what we call ladder, right? Even the smallest large model, you're looking at hundreds of millions of parameters, right? And for the largest model, you're looking at over 100 billions of parameters. And then the number of chips will just scale up, right? So now think about it, you probably need not only 1,000, but tens of thousands or even millions of just 100,000 or to millions of cards in order to just support a large, diverse research, because each of them would require a non-trivial amount. Each research thread in this would require a non-trivial amount of chips, right? So even within Google, I would say chip is something people would be fighting for. All right, here I would like to thank the entire team. Probably there are some other people not listed there for the year 1.6, but yeah, it's truly a teamwork. Now you would have people who are working for just to make sure our data infrastructures are right. There are people who want to make sure that when we want to do real robot evals, we can have a setup and the robot is ready, right? And there will be people who are looking at tuning the different recipes. There will be people looking at to see if my data is the right data that goes into the model. Right? And there will be people who are also responsible for, like my team is like, is the humanoid doing, if the VLA is doing the right job? Is the robot stumbling, or is it reliably executing the plan, right? All these different aspects. That's why we have a large team that covers all the different aspects. Yeah. Okay. And thank you so much for listening to this talk. And if you have any questions.
Any questions from all the guests?
Yeah, thank you for the great talk. It's very impressive. I have two questions. First one is about the multi-embodiment generalization. So is this VLA model also can generalize to on-scene?
For that part, I have to check, because my understanding is that it can. You just need to provide that new embodiment data. But for how much, I don't know.
So what do you mean by provide the data? You can provide the condition or include the data in the scheme?
Well, you still need to you definitely need to fine tune on this, yeah.
Yeah, thank you. The other question is the Aloha demo, the agentic long paradigm function. So are you guys also using some of the Python language or just a natural language for the?
We use only natural language.
Okay. Thank you.
Hi. Thank you for the talk. I had a question about like data generalization. Like you mentioned, compute is expensive, data is expensive, and how do you think? So my problem is like if we have a couple of arms and a camera, but if the camera position changes relative to the arms, it will obviously change the perception of the spatial environment. So going forward, do you think that it is wise to have a single model that generalizes for all embodiments, or do you think there should be like a distributed like stack where one stack is just calculating the position of the robot arms with respect to sensing and stuff like that, so that the reasoning is generalized for like a LLM, and then the physical tasks are done by a planner or something like that?
I would say actually even today we saw some kind of generalization that's already there. For example, the ER model, none of these pictures are from the same camera, right? So essentially a lot of these pictures are coming from internet. I don't even know how they capture that, right? And it's able to pinpoint in the pixel level to see which is which, right? So at the higher level, I think they are generalizable to whatever your capture device. Maybe the fisheye camera would be difficult, but you can rectify that. And then at the VLA level, what we found is that these models are not extremely sensitive to camera calibrations or intrinsics. Right? You can camera intrinsics that are pretty off and they still work. Right? As long as you don't flip in a very weird way, right? Like rotating 45 degrees, and then that might be an issue there. But then again, with the humanoid, what you can say is like it's beautiful, it's changing all the time. So it's it's still there. But once you have, I would say it's the same thing. You have enough diverse training data, it kind of can figure out things by itself. But of course, if you have high quality post-training data for a particular task, you will improve its efficiency and success.
Yeah.
First, and then the other third
Yes.
voice.
Yeah. Thank you for the talk. And you mentioned a little bit more about like the quality of the data. And so in this like a data-driven perspective, we are kind of teaching the model, the procedure or the decision-making process of human through the data. And so my question is like, do you observe there are any like decision rules that are very hard to teach the robot to do just using data? If it is true, then is there any way we can add some role-based method into the decision-making process of this like a data-driven model? If that is a clear question, yeah.
Well, here's the thing, right? If you're talking about a decision, you're talking about almost the planning orchestration part, right?
Or sometimes it is also low level. I mean, if we train the robot to pick out the bugs to somewhere, and there are some like a criterion we'll make where we should switch to next motion or next phase, and those are based on some decision embedding our brain, but we need to somehow transfer this decision-making role through data to the model. And is that easy to transfer this kind of role, or there are some kind of role it's really hard to transfer just from data? We need to.
It's hard to know at this stage, right? So, for example, what I can say is the FSD from Tesla is kind of end to end, right?
Yeah.
And there are going to be long tail distributions that you might not be able to capture. But once you have like billions of miles of data, then it's hard to be OOD, right?
Okay.
And maybe once you can train on all the internet scale of human collection data or some source, I don't know exactly, then maybe you no longer have the issue of OOD, or maybe you still have some long tail or rare cases. But in that case, as long as the model is not doing something weird, maybe you can just, maybe we accept that this is the life, right? Sometimes we also are confused by our decisions on what should we
That's true.
do.
Thank you.
Yeah, so the objects which are dynamic through time and space, whether that be like literally water that needs to cool down and cool it or maybe a car that's rolling across the sea. Have you tested any of your models on something like that?
No, not yet. Okay. So right now, I don't think that's the focus that we want to test, right? Maybe, so as again, I feel this is also a scaling problem, right? So it's like the self-learning. Once you have enough data, then most of these things won't be too big a problem.
Okay, thank you.
I'm not sure if you can answer it from a technical basis, depending on how much you can say, but when you train for cross embodiment, do you train the full BLA, or do you add some, say, retargeting head that is then adjusted for embodiment?
So first, the data is collected by each individual embodiment, right? So technically, you don't need to do any retargeting.
I meant like specifically when you do cross embodiment training, you have all the data already.
Yeah.
But do you train the full model, or do you say train just a specific like retargeting head only?
No, we train the full model.
You full train.
Yeah, that's a single model. Yeah.
I see.
Yeah. My question has to do with you mentioned collection of data from the internet, for example. How do you deal with varying levels of expertise in the data that's collecting? Not all the data is going to be, or they're not going to be very good at doing the task, but there's a lot of inverse reinforcement learning that has specifically addressed that. I don't know if you could talk a bit about that.
Yeah, for data, so data quality is a pen, right? So for anyone who's using data, so we do have QC process for the data. So at least for the data that are pretty bad, they should be filtered out, right? So, but for the various expertise, and then you have to define, I would say for some of the tasks, if you really care about high nines, then for this post-training task, you really want them to be as clean as possible, right? But during the pre-training, usually diverse data is often not used.
And I guess the follow-up, should we not use suboptimal data whatsoever? Is there no value in?
No, we use.
Okay.
Yeah. So again, in diversity, because partially It's like we can't watch for, if you have a lot of data, there's no way you can watch for every single episode of them, right? So I'm pretty sure there are suboptimal data there somewhere, right? But how much and how they impact, that's something that we do have to do more applications there.
My question is like human factors a little bit. In one of the goals, one of the KPIs was like safe interaction rate. I guess my question is any of the goal like thinking the robot thinking about how humans are perceiving them? Like for example, it was able to track like the fastest way from like the end of the living room to the other end of the living room, kind of like between the futons. But like, what if people are sitting on the couch and watching the TV there? Would it know to go the other way? Like, I'm just thinking, like, are there human factor considerations in a lot of this yet, or like?
I think for this particular stuff, if you depending on how you prompt this, I think you can get this kind of social behavior out of that as well. Yeah, you can say maybe now you say I want a trajectory, but I also want to be respectful about the private space. Then you can give it a try, right? The models are there, especially for the ER models. I believe they are more publicly available. You can just try to see what they come up with, right? I believe there are certain of this knowledge are also built in there, right? But how good it is, or do we have enough coverages during our tuning? I don't know. That's a good question, though. Yeah.
I was just wondering, for the picture where you had kind of like the breakfast with the coffee and the bowl they had in one of your slides, if, for example, the coffee was in the path of that you had firstly made for to get the bowl, would the model be able to comprehend that, like, hey, I have to be careful for this because I don't want to spill this?
You have to be, you mean the coffee in the bowl you want is so
would it avoid the coffee to pick up? Would it know to avoid the obstacles? What I'm trying to ask.
To a certain extent, yes, these are building behavior, right? So for example, they are when they are moving. So because moving our teleop data, you would not have the reflex smash
right
onto this coffee, right? But to how much they learn to increase avoid that part, I don't know.
Okay, cool. Yeah, thank you.
Have you tried completing a task where one of the arms is an Aloha arm and the other one's a Frank arm? With that configuration?
We don't have that. That's a good. I think that's something that academia can try, right? For us, there is an issue that for each of these hardware platforms that we support, there's a cost. And then mix and matching, we have to make sure the driver is ready, and we have to do a whole bunch of things just to make that platform ready.
When you're wondering robots, so what kind of object are we using? Like, I guess this is kind of like so
inference?
Yeah, inference on the
no, we don't. These models are not inference on robots. They are served in the cloud.
So direction that you get.
Well, certainly we'll be interested, but they may not be our top priority. Because if we can get our best model work, then we can just say, now it's not our job to make it work in embedded system, right? Not much of our job to figure out all the optimization of the things. For us, it's more of the capability first. Then optimization comes, it will come naturally because there's a demand.
Last question.
Okay, yeah. So it's not limited to VLA, but a generalist robot question. So how do you see us incorporating other modes of perception? For example, force, torque, tactile.
Yes.
Yeah, is it more in the end-to-end manner you see in the large model, or do you see it in the more kind of modular hierarchical like?
I think some of them it really depends on where they're coming to, right? So for example, the VLAs they're being designed to run, but not at a very high frequency. That means it may not be able to leverage some of the faster reactions. You have to build it probably at a little bit lower level. Like humans, well, we have a thing called the cutaneous reflex. So what does that mean? It's like you step on a nail, you suddenly retract, right? And that is without we think about it, right? So these are very low level. They are actually even sometimes below. They are actually below the spinal reflex. They are even at the local motor neurons, right? So we do think some of this information should be built more. Essentially, we can build more intelligence, maybe leverage torque and force it into the lower level controllers. So they're more compliant, they're more safer, etc. Right? And then for some of the other modality, there's a question. Maybe a tactile or something we can build into these VLAs just because, depending on how you measure that, they can have a similarity as images, right? So, but if you have a modality like EMG, then if it's nowhere you can find this data in internet, then you don't benefit a lot from them. You're essentially looking at a completely different modality that has very scarce data, right? So if there's a data that you can assimilate them or making them in a way into a known modality, then they probably are going to be easier to use. For example, maybe with some of the stuff you can say call them as a tool. Then you can say the tool will return you either image or some natural language to describe what's happening there, right? Rather than directly feeding them into the model. The model probably will be very confused on what happens there.
Yeah, I know folks have many other questions. I think Dr. Zhang will be here a little bit longer until we move to the next location around 4:30. But yeah, let's thank Dr. Zhang for the one.